welcome to the second session of Physics Talk 2021. I am Mohammad Abdusani Akondo, a junior student in Physics discipline from University. It is my great pleasure to introduce our speaker, Abhijeet Dutta. He is currently a teaching assistant in Department of Physics, Brack University.
Yeah, thank you very much to all the organizers for arranging this wonderful webinar. I'm sorry for this delay. I faced a Wi-Fi cutout today. It's really unfortunate because it was like I was notified like at 3 p.m. that the fiber optic cable that came to my home has cut off, and then now I'm using some other resources. Don't ask me why. And I'm very sorry that I can't share my screen, my video of my face, because literally I'm standing on a field with a torn out shirt and just speaking. Okay, so I hope I'm as informal as you can like. So feel free to ask any questions. Here we go. So it's a topic about um, um, critical phenomena and field theory. Um, critical phenomena and field theory. Okay, so what do we mean by critical phenomena? Is that it is a point where a phase transition takes place, but it's a very it's not just that. There's something very discontinuous happens. Okay, more precisely, the response functions blows up at this point. Okay, where do we see phase transitions? Phase transitions can be seen for liquid gas transitions, everyday phenomena like liquid solid transitions, Ferromagnet-Paramagnet transitions, and many other things like superconductor transitions and all that, normal state, superconducting state, and all that. So this was the business of like material science or like time memorial, and also in the business of condensed matter physics, as you can easily understand from my initial few examples, are also the name of phase transition. Lately, due to some remarkable achievements in the 1960s, 70s, people trying to understand quantum field theory better, Kenneth Wilson, Liu Kadanoff, first of all, came up with the idea of a block spin renormalization procedure, which made people understand how Ising-like model of magnets can generate phase transitions. Then Kenneth Wilson came in and actually taught us how to realize the renormalization procedure. The people who are actually hiding the infinities out of the work. In quantum field theory calculations, we find a lot of infinities coming out, because a lot of actually in a sense, and the infinities come up and they come out a lot. Or whatever you calculate, you get the infinity. Okay. So the reason is that in quantum field theory, a local operator is defined at a point. So they call local fields. And you see the interaction terms will be like, say, polynomial interaction terms will be like powers of this field. So at a particular space-time point, and these fields are actually distributions. Okay. So what happens is distributing fluctuating fields at each point in space-time, and you are taking like two fluctuating fields or distributions at the same point. Now it's a very bad thing to consider. Like you can think of it like a delta functions at the same point, two delta functions at the same point. So it's not a very good idea, and it's already divergent by its own nature. Okay, these kind of things actually gives the idea of interaction at a point. Okay, say some particle is coming at this point, some other coming in this point, the electron or positron coming in, so positron, electron coming in, and then annihilating photon. So it's like 3-point interaction. So there's like, okay, so you can say psi, and like an mu field with a gamma mu inside, just to be precise about this interaction term. So what the important idea is that this is a local interaction. Okay, so all the fields, there are 3 fields like psi, and mu, they come and meet at a point. Okay, so at a point, all the 3 fields, and they're fluctuating fields. So you're supposed to get something very bad at that point, because they're distributions and you are evaluating a few distributions at the same point. Okay, so that is the whole idea of ultraviolet divergence in quantum field theories. Like if you probe short distances, so at a point means it's very short distances you are probing. We're in physical example would be like we're trying to probe the nucleus, and inside there are quarks, and we are to understand the structure of nucleus or protons or quarks. Okay, we go deep beyond, we scatter them, deep inelastic scattering, and all these experiments we do, we go higher and higher energy, and that means higher energy means higher momenta, and from uncertainty principle, higher momentum means short distances. So we try to probe short distance physics, and we get this divergent behavior because short distance physics are too local, okay, and the momenta is too high, okay, too high. The momenta too high means it actually blows off. So this is the idea of well, the scattering amplitudes blow up, and don't mean that we are actually probing infinite energies. But what happens that when we try to calculate experiment, in the calculations, we are actually saying that we are আমরা আসলে infinite momentum calculate করছি। ক্যালকুলেশন আমরা ওটাই বলতেছি, এক্সপেরিমেন্টে আমরা ওটা করতে পারি না, বাট ক্যালকুলেশন যখন আমি বলছি যে কয়েকটা ফিল্ডকে আমি একই পয়েন্টে ইভালুয়েট করছি, স্ক্যাটারিং পয়েন্ট, so in the calculations we are actually assuming that we are actually doing the experiment the same point, okay, so in the calculations we are doing that mistake, so it's continuum thing or something, so that's why we're getting this divergence, okay, and getting divergences all over the place, okay, so that was the thing which was not philosophically clear. People knew how to handle this infinity by some regularization techniques. Dimensional regularization came in 1970. Before that, there were Pauli Viller's regularization available, but people didn't know what they were doing actually. Okay, they're just hiding some infinities. Okay, so what they were actually doing, okay, new whiteboard. What they're actually doing is that there are some parameters in the theory, like the mass is a parameter. Sorry, mass is a parameter of your theory. Charge is a parameter. So let me call. So these things can be called as couplings. So in general, couplings can be called like G1 or G2. Okay. So other couplings can be present, but for example, say for QED, there are two couplings in the theory. Okay. So what the procedure is that the theory that I start with, say by theory we mean the Lagrangian. The Lagrangian for the field theory that we start with. I'm sorry, I had some better ideas for this talk, but unfortunate situation made me force this. Okay, I hope everybody is familiar with Lagrangians or soft Lagrangians. This is a soft Lagrangian. All right, so if at any point in the talk, if you have any questions, just shoot. If you don't understand something, I will just go on and try to explain that. Yeah. So you see, pretty much I had a script ready, but now I am outside without the script. So it's wherever I go or wherever direction your question leads to. Okay, so you're free to ask questions at any point. Yeah. So in this theory, say okay, say scalar electrodynamics. So I have something like say so I should have given this phi mod square. So these are like say phi mod square because আমার তো আমি যদি ইলেকট্রোম্যাগনেটিক ইন্টারঅ্যাকশনের কথা বলি স্কেলার ইলেকট্রোডাইনামিক্সে আমার কমপ্লেক্স স্কেলার ফিল্ড লাগবে, so say phi star phi coupled with how am I going to give this there will be some index there, there's some constant potential, for example. Let's shall I go with the I'm not sure where I'm going. This is gamma matrix. Anyhow, let's just consider something like this. It's not important. What is important is that there's a coupling here and there's a coupling here. Okay. Some 3-point interaction out here, something like that, for example. So here there are mass terms and there are like E. These are like couplings. Mass generally couples to quadratic of the field, and E generally couples to the coupling of other fields. That tells you the interaction term. Okay. So so what happens that in the calculation, if you suppose you want to calculate the scattering amplitude of phi with phi, so there are two phi's and come in and two phi's go out. Let's say this kind of interaction, and I want to calculate say higher order diagram, higher order processes of this. So the phi comes in and phi goes out. Okay. মানে হচ্ছে ধরো ধরেন so this is like a meson scattering. So this is a pi meson, this is a pi meson scattered into a pi meson and a pi meson. Okay. So but it's a cubic term, so I can also have something like okay, not like that, say this a loop and this. Okay, so this is a cubic interaction, some okay, but this If I bring in two particles, can I? So I have to like, okay, can bring in two particles, come in. Yeah, two particles go out. Okay, so these processes can happen. So this is like a blob. With high energy experiment, we can get terms like this. So this is an example of phi cube theory, because at the vertices there are like three fields. Okay, three fields are meeting at this point. Okay, I can also have examples like phi 4 theory, which is something like this. And for this, there is like a momenta, internal momenta q, যেটার উপর আমাদের integrate করতে হয় to find the scattering amplitude. There is a propagator here, there's a propagator here. So there are two propagators. I'm dropping other external momenta, only the relevant internal momenta over which we have to integrate using the Feynman rules. So after using the delta function, we have these two propagators, and for the scalar fields, the propagators go like q squared. Let's drop the m squared term, which is not important for the moment. I'm just talking about how the divergences come in. So this goes like q to the power d minus 4. Okay, so you can see this is an integral which is for quantum mechanics tells us যে এখানে কি হইতেছে আমরা জানি না. So you have to মানে this momenta, this is a momenta. Okay, so because we don't know what is happening here, we have to consider all sorts of moments. What does that mean? From infinity to minus infinity to plus infinity. That is the quantum mechanical superposition principle. Okay. So you can see from this expression that this will blow up. Okay. Because it's infinity. It will be divergent whenever the dimension is greater than 4. Well, greater equal 4. If you have so it will be logarithmically divergent. Or okay, wait a second. No, greater than 4. Yeah, I think I was messing up something. Greater than 4, because q to the power 0 is like constant. So d greater than 4, you will get this divergent term. Okay. Yeah, because I'm writing just this term. Inside there'll be some logarithm if you have this 4 there. Integration code would get some logarithm, but anyhow. So these divergent terms are these things come up whenever you're going for like higher dimensions or something like that. Okay. So what do we do to hide these divergent terms? Okay. So people যেটা করে যে there are parameters in the theory for like the mass. Okay. So they redefine the mass, something called physical mass, which is so this is the bare mass যেটা নিয়ে আমরা Lagrangian লিখছি. We started the theory. This is definitely not the mass which we see in the experiment, because আমরা যে theory লিখতেছি initially, that theory has nothing to do with experiments, right? This is just what you're writing. Experiment, so renormalization idea is actually it connects to experiment. Okay, so physical, this is the philosophy behind that, and there is something like delta m. Okay, so this is the bare mass, this is the physical mass, this is the mass which we actually see, and this is this some other thing. Okay, যেটা আমরা, okay, this is what we introduce, this is a transformation that we introduce, and this is called RG transformation. So this soaks up the infinity that came from the previous okay, so this soaks up the infinity that came from this process. Okay, এখান থেকে যে ইনফিনিটিটা আসবে, I can soak it up in the mass term. Okay, or in this case actually well, to be more precise, in this case this should be soaked up in the coupling. In this case this should be soaked up in the coupling rather than in the mass, কারণ mass basically comes from 2-point function থেকে আসে। তো এই লুপের কন্ট্রিবিউশনটা mass soak up করবে, আর এটা soak up করবে হচ্ছে 4-point interaction because this is like g phi to the power 4 interaction. So this will soak up the infinity coming from here. Okay, and this will soak up the what should I say correction, infinite contribution যে scattering থেকে আসবে সেটাকে I can soak it up inside the mass term, and I say এখানে একটা minus infinity আছে, this plus infinity, they cancel out, and this is what we don't calculate from our calculations. Okay, we assume that physical masses are something that are in nature. Okay, they are physical parameters that we know, like electron mass or electron charge or pion mass, or well, pions are charge neutral, but anyhow. So yeah, but there is other kind of charge out there. So coupling out there. So yeah, so we say basically okay, we renormalize the parameters. Okay, renormalize the parameters, these things, such that we get sensible answers. So the infinities of these loops gets absorbed into these parameters, and we end up getting a finite result. And people won Nobel Prizes for that. So that's successful. Okay, that was successful. But so what it so this was okay. before 1960s, 70s, but people still didn't know what was the rationale in your theory. So you see, in a Lagrangian theory, um, terms like I'm not caring about the sign here. Um, these are minus signs and plus signs, but let me try. Minus. There can be other terms like these are potential called B of phi potential terms, polynomial interaction terms. So I say G1, this is G2 phi to the power 6 terms and all that. You can already see I'm already adding the quadratic terms, assuming there is a rotational symmetry in the theory. But what we see, J nature, we say the negative mass dimension. So these things have a mass dimension. Mass dimension is defined by the action is written like this: d4x Lagrangian. Okay, so this has a mass dimension -4. I'm doing explicitly in 4 dimensions. Action is massless. This has dimension 0 because I am working with h bar equal to 1. And what is the dimension of Lagrangian? So because action is massless, this dimension must be +4. Okay, because d4x is dimension -4. So these are a mass dimension. And okay, is everybody familiar with the idea of mass dimension? Hello? I hope
No.
they are. No. Oh. Oh. Okay. Probably I shouldn't have asked the question. Okay. So the idea is okay. So the mass dimension idea is that energy and mass they have the same dimension. If c equal to 1, e equal to mc square, and e is also equal to hf. Okay. F is like 1 over t. H is 1. So um, it has the energy has the inverse of time dimension. So energy is mass. Mass has the inverse of time dimension. What about length and time? Well, length by time is c. C equal to 1. That means length and time has the same dimension. Okay. So আমরা যদি length কে দেখি, length কে আমি দেখবো it has a length dimension like 4, but এটাকে আমি mass dimension এ convert করলে that should be like -4. Is it okay?
Yeah.
Okay. So is there a way to erase the whole board except for manually doing this? Trying to okay, so yeah, okay, that would be all right. So from here, so এখানে আমরা দেখতে পাচ্ছি যে phi এর mass dimension কত হবে. So phi mass dimension if you calculate, so for in general if it's a d dimension, the phi mass dimension you can take it as a homework and calculate that this should be turn out to be d minus 2 by 2. Okay, and in 4 dimensions this should be like 4 minus 2 by 2, that is 2 by 2, that is 1. So you see যে এটার mass dimension তাহলে এই টার্মে phi আছে দুইটা. So phi has dimension, as I said, in 4 dimension it would have dimension 2. That means 1 1 2. Phi square has dimension 2. So mass should have dimension মানে m square is actually mass term. Okay, এটাকে আমরা originally মানে suppose we don't know what it is. Okay, then we want to find out its dimension. It turns out to be m squared, মানে mass dimension squared. So we assume we then say that okay, it's a mass. Okay, can act like a mass. There are other ways to understand why mass term is that, but generally mass term is something which couples to quadratic of the field. So and this part is like the part which gives you the propagator part. Okay. All right. And this is the coupling. So 8 dimension coupling. So can anybody calculate the dimension of G just from this analysis? J S have to be that whole thing has to be dimensionless. So this is like minus D in D dimensions, say, or even in 4 dimensions if you want to do. Okay. So it has dimension say minus D, then Lagrangian should have dimension D. From here, please find the dimension of G. What would you find?
That will be -4.
Well, in 4 dimensions, this is dimensionless, right? Count 4 dimensions, so phi at dimension 1. So there are 4 phi fields. Okay. If I'm not talking about loops, the interaction term would look like this. There are 4 phi fields coming and interacting at the same point. Right? Okay. So physically বুঝতে গেলে like two particles incoming and they're interacting at a point because this is a quantum field theory, and that's the thing I was like saying for a long time. Like this is 4x at the same point, and like this, right? All right. So yeah, so the four fields, they all have dimension 1. So আমার Lagrangian যেটা ছিল, okay, my Lagrangian was this, and my Lagrangian 4 dimensions same. Lagrangian should have dimension 4, so that is taken care of by the 4 5 fields. Okay, তাহলে আমার G এর dimensionless. Okay, so dimensionless G is okay, but এর উপরে যে 5 6 টার্ম গুলো আছে, so you would guess যে ওদের ডাইমেনশন নিচের গুলো যে প্যারামিটার গুলো আছে, ফর এক্সাম্পল মাস এর ডাইমেনশন পজিটিভ মাস dimension 2. G is dimensionless. Higher order term যেগুলো আছে, they would have negative dimensions. Okay, now negative mass dimensions are bad. Okay, why they are bad? Because if you calculate the scattering amplitude, if you do the analysis with the scattering amplitude, okay, for negative mass dimension, for let's say 5 6, when you calculate the sigma cross section, they will go with some power of energy. Okay, so আমরা জানি যে scattering এর sigma cross section gives us the idea of probability. Okay, so this cannot like grow, it cannot grow with energy. Okay, sigma goes like 1 by e is okay. We expect something like 1 over e or 1 over e squared or something like that. We don't expect sigma to go like e or some power of e. Okay, so if you do the analysis with negative mass dimensions of coupling, you'd end up getting this kind of situation. Okay, the mass dimension would contribute to the sigma, and you see the sigma actually grows with the energy. মানে unitarity violation বলে এটাকে. Technically people say this is a unitarity violation. Okay, so that's one way to see why. There are two things, but this is one way to see why we don't in particle physics experiment or high energy physics things, people say যে কোনটা relevant আর কোনটা irrelevant. So in low energy, আমরা যদি low energy তে কাজ করি, তাহলে we say that okay, these things are not relevant, this is relevant. Okay, this piece is relevant to our physics, and the higher 5 6 5 8 terms, they are not relevant to our physics. Is this idea clear? Does this make sense? This is a hand waving argument, but yeah, I'm not trying to give a particle physics talk here, so yeah.
দাদা একটা কোশ্চেন করা
Yeah.
যাবে?
Yeah, sure.
আপনি এখানে এই যে খালি ইয়ে পাওয়ারটা নিচ্ছেন তাই না, ইভেন পাওয়ারটা নিচ্ছেন ফাইল উপরে?
Yeah, because I'm considering asymmetry here.
আপনি ইম্পোজ করতেছেন জেড টু সিমেট্রিকে ইম্পোজ করে দিচ্ছেন ওই জন্য জাস্ট এখানে জেড টু সিমেট্রি দেওয়ার কি কোনো রিজন আছে নাকি জাস্ট এমনিতে?
Well, তুমি তো 5 cube theory দিলে your vacuum would be unstable, right? 5 cube theory would have something like a cubic type of term. Yeah.
যেমন না ওই 5 টু দি পাওয়ার 6 যখন অ্যাড করলেন, আমি তো একটা 5 টু দি পাওয়ার 5 ও তো অ্যাড করতে পারতাম, রাইট? একটা পসিবল কম্বিনেশন যে ইয়েতে নন রিজনেবল হলেও তারপর আমি ওয়ান ওয়েতে লেখা পসিবল, রাইট? ইউকা পটেনশিয়াল আমি খালি একটু কনফিউজড যে জাস্ট আমি জেড টু সিমেট্রিটা দিচ্ছি, ইম্পোজ করতেছি আমার ল্যাগ্রাঞ্জিয়ানে, দ্যাটস ওয়াই আমি খালি ইভেন পাওয়ার বলে নিচ্ছিলাম, তাই না?
Yeah, it's not actually well. So well, if you think okay, so yeah, actually okay, so I assume the rotational symmetry here. Okay? Yeah, you can add them up. It's for simplicity I did that. Yeah, তুমি চাইলে তোমার থিওরিতে ওই সিমেট্রি না রাখতে পারো। So this is a yeah, that's a good question, by the way. So if you have a okay, so if you add, so this is a good point that I can talk about a bit. I can't add more than 12 whiteboards. Okay, so initial things I can delete. Okay. I probably shouldn't have deleted that, but anyhow. Yeah, so I can probably say a few things about that. But why I can't have another whiteboard? A new whiteboard. I'm sorry. I'm just always clicking. Oh, I was stupid. Sorry. I was clicking view all boards and I'm not clicking a new board. So I'm not supposed to get something new. So আমার theory একটা 5 cube term থাকে. So this term, so what happens if your theory has a 5 cube term? Okay. So if your theory has a odd power term, so এই ধরনের 3-point functional normalization এর জন্য, so this will contribute a term to 1 point, একটা 1-point function যদি calculate করা হয়, okay, say something 1-point function, how should that look like? So this is a 3-point function, and this can contribute something to a 1-point function. So I don't know how to yeah, something like that. So this will contribute something to this point. Okay, it's like 1-point function. So this 3-point function will have a contribution to this 1-point function if you do the renormalization. Okay, কারণ তুমি তোমার থিওরিতে এই টার্মটা রাখার কারণে মানে so if you exclude this theory this term will not be there, this term will not, মানে তুমি যদি অড পাওয়ার না রাখো রিনর্মালাইজেশন কিন্তু ওই টার্মটা জেনারেট করবে। ওকে, তুমি তোমার থিওরিতে যদি সিমেট্রি বলো যে আমার থিওরিতে শুধু ইভেন পাওয়ার্স থাকবে, তো রিনর্মালাইজেশন উইল নট জেনারেট কাউন্টার টার্ম। ওকে, এই প্রসিডিউরের মাধ্যমে রিনর্মালাইজেশন ট্রান্সফরমেশন করে you will not get terms like 5 to the power twice and plus 1 which is contributing to some 5 to the power 2n diagram contribution. Okay, Shumit, so this is one of the ideas why I was not introducing those 5 terms.
Thank you, Dada.
That was okay. That's a good question. Oh, there is an option for deleting this, maybe. Clear my drawing. Clear my drawing. Okay, so this move it. Okay, so that was so negative mass dimension of the coupling causes one trouble with quantum mechanics, that it actually violates the probability or unitarity. Another problem well, so another thing, it's not in renormalization what it does is that there are the notions of relevant and irrelevant and marginal coupling. So that I'm will like to explain with a model. So let us start with a model. So we talk about the partition function. I think is everybody familiar with the idea of a partition function? I'm assuming if the silence persists for more than 3 seconds, I'm assuming this is okay. Everybody's familiar with the idea of partition function. So initially people use the idea of partition function to normalize the probabilities. So you calculate the probability for a Boltzmann distribution at a particular energy state. Okay, how many particles are there? So you calculate this thing and you have like minus beta EI probability, and you normalize this by dividing it by the something so-called partition function. It's a normalization of sum of all probabilities. Okay, so probability factors. So probability factors are e to the power minus beta EI. Okay? So initially we start the idea of partition function to be this. Okay, then okay, so this is the starting of statistical mechanics. That's why people like call it starting of statistical mechanics. I'm not sure, or maybe that's why people call Boltzmann the father of statistical mechanics, because later people figured out that Z actually contains everything that you need to know. Okay, all the thermodynamical macroscopic variables like pressure, entropy, they all can be calculated from partition function. So if you know the partition function of a statistical mechanical system, there are formulas, okay, that you can use to calculate everything else, like free energy, you know, everything else. Okay. All right, so that's the short intro about partition function. Now here we're going to use in quantum field theory or quantum statistical field theory a Z, and we are calling it a partition function. Quantum field theory in path integral we call this generating function, but that's the same vibe as people do in probabilities, like moment generating function is actually does the same. Okay, so fast moment is like expectation value, okay, like mu. Second moment is like standard deviation or fluctuation, and other moments are there. So okay, cool. So that's behind the name. Now okay, so the partition function will be to the power minus s. Okay, so has dimension, s is dimensionless. Why? Because I'm considering h equal to 1. Euclidean, if somebody wants to talk about this in field theory language, it's called Euclidean quantum field theory or Euclidean field theory. Okay, so what we have done here is that quantum mechanics or path integral approach, amplitude goes like e to the power I s by h bar. Now if you weak rotate, so s is nothing but quantum mechanics korchi, so say dt Hamiltonian, sorry, well Hamiltonian or Lagrangian. Hamiltonian to the interaction term bole debi same with the sign tab, but okay, so you would understand connect a sign difference with the Li is equal to minus hi because of Legendre transformation. So you would understand. So what I'm doing here, I'm doing a weak rotation. So t goes to I tau. Okay, so this term would become e to the power minus I s by h bar. But if you take h bar equal to 1, you get e to the power minus is. Okay, that's what I've written down. So one way to people talk about it, time evolution operator. which is u, which goes like e to the power minus I h t under weak rotation. That means you complexify or analytically continue your time dimension, and you end up getting something which is something of a thermal field theory. Okay, or if you give a minus sign, it's a minus. Something thermal field theory. Okay, so এটা হচ্ছে quantum mechanics, and this is something like finite temperature field theory. So that's a neat connection between yeah. Right. So okay, so I think this is clear to everyone. Then let's move on. So so আমি field theory জন্য লিখছি, so I have a field configuration phi. Let me start from a step notch, one notch down, not start from there. Let me so let's start with some points on a lattice. Say okay, so these are there, so every point has a spin variable si. That means Ising, some sort of Ising model, model of a lot of spins. Okay. So so there is a lattice passing, that is A, and how these spins correlate with each other is given by a correlation length. Okay, and if the correlation length is large, okay, if it is large, okay, that means I have a large order in my theory. তার মানে একটা স্পিন অনেক দূরের একটা স্পিনকে এফেক্ট করতে পারে. Okay, if okay, so you can understand the situation I'm talking about is like less than, so basic idea টা আমি দিচ্ছি যে t greater than tc তে you would see spins point all over the direction. Okay, thermal agitation will just destroy the symmetry. Well, not destroy the symmetry, restore the symmetry. মানে এখানে এই জিনিসটাকে আমি যদি ইচ্ছা মতো রোটেট করি, okay, this is not an Ising model basically, but in Ising model there is like only up or down, but this is a like ferromagnetic model or Heisenberg model. So in that model, so this is the picture which I've drawn here when talking about a Heisenberg model. Just illustrate the point that you know that Curie temperature উপরে, if you have bunch of magnetic dipoles, they will point in arbitrary dimensions. Okay, arbitrary directions all over the place. Okay, and as a whole, if you rotate the whole thing, মানে যেহেতু average magnetization 0, if you rotate the whole thing, the configuration will almost look the same. Okay, because statistical mechanics language, there are many microstates corresponding to that macro state. Okay, so that's why this is happening. Okay, but if you lower the temperature, what happens is these spins align. Okay, and there is a spontaneous magnetization goes on. Okay, so you are in paramagnetic phase, and then you are less than the Curie temperature, you are in the paramagnetic phase. You would not expect a large long range order. Okay, একটা স্পিনের সাথে আরেকটা অনেক দূরের স্পিনে কোনো কোরিলেশন থাকার কথাই না. They are pointing in different directions. Okay, okay, they're like eons far. But যদি t less than tc হয়, okay, or you put an external magnetic field and they all align, then what happens that they have a strong they can have a strong correlation. Okay, so that's kind of thing we are kind of assuming here. Let's say the number xi has a large correlation, that means it's greater than 1, the large correlation. Then what you can do, because that আমাদের যেহেতু ল্যাটিসটা পয়েন্ট দ্বারা গঠিত, so the lattice has this granular structure, okay, site like structure, spins. Okay, but we can use a field to describe this thing. Even though it has the site like structure, we are going to use a field, a slowly varying field. Okay, slowly, nothing much happening, slowly varying field to describe a situation like this. Okay, okay, I hope that this is the philosophy behind why we're considering something like field theory, integration over d phi, or why the phi came in. So we are approximating this picture by a phi. Okay, is it clear? Some of you would be able to notice that there is a symmetry breaking going on, so everything in the same pot here. Like spontaneous symmetry breaking, phase transition, field theory, critical phenomena, they're all the same pot. Yeah. All right, so let's just start doing what so I think nobody has any complaint on this one. Okay, so S is the action. Oh yeah, oh my god, sorry. Yeah, I got startled completely.
আমার ওই যে ওই পয়েন্টটাতে একটুখানি সমস্যা হচ্ছে আপনি এই যে
Yeah.
phi x দিয়ে যখন এটাকে অ্যাপ্রক্সিমেট করলেন, x
Yeah.
কন্টিনিউয়াস একটা ভেরিয়েবল, রাইট?
Yeah.
কিন্তু আমার যখন ওই প্যারাম্যাগনেটিক মানে স্পিন গুলা ছিল, এটা জাস্ট পয়েন্ট টু পয়েন্ট ডিসক্রিট জিনিস, রাইট? এখন phi x কে তার মানে আমার মানে আমি x কে ভ্যারি করার সাথে সাথে আমার phi
Am I
x
saying it wrong way around? Are you saying I'm saying the wrong way around?
না 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 মানে আমি মানে এই phi x কে কিভাবে করে মানে ইয়ে করতে পারলাম, মানে আমার তো একটা সিঙ্গেল পয়েন্ট স্পিন ছিল, রাইট? জাস্ট একটা পয়েন্টে, যে কোনো একটা পয়েন্টে ডিসক্রিট পয়েন্টে মানে আমার
Yeah. Whoa. Yeah.
মিন ভ্যালু অ্যাপ্রক্সিমেশন ইউজ করলো মানে কতখানি
Yeah.
পর্যন্ত
Yeah.
আমি এটাকে
Okay.
ইয়ে
So
করছি,
yeah.
মানে এই পয়েন্টটা ক্লিয়ার হচ্ছে
Okay.
না
So
আর কি,
that,
মানে phi x এর আমি যে
yeah.
এটাকে
Okay.
অ্যাপ্রক্সিমেট করলাম।
Acha, so yeah. Okay. Yeah. It's
phi
kind
x
of
তো
a
একটা
mean value.
কন্টিনিউয়াস জিনিস, x তো আমার
Yeah. When I
কন্টিনিউয়াসলি ভ্যারি করতেছে, বাট
say you have you have 4 lattice points, suppose. Huh? So I am like averaging those spins. Okay. And instead of 4 lattice points, I'm just substituting this. What you said is what I'm doing there. Mean field theory approximation. Yeah, আমি স্পিন গুলো নিচ্ছি, আমি কোর্স গ্রেন করছি এগুলোকে।
হ্যাঁ
মানে
আমি এভারেজটাকে কাউন্ট করতেছি কি, রাইট?
So I'm actually averaging it, yeah, and I'm calling that as a phi x. মানে আমি এখানে যে ইনডেক্সটা আছে ওটাকে আমি
সেটা হচ্ছে কি আমার phi x দিয়ে আমি ডিনোট করলাম।
yeah, so something average going on here.
Yes.
Yeah, it's some continuum limit, yeah. Okay. So yeah, that's exactly what I'm doing. Yeah. So so z is like d phi. So s so what I'm going to do here, I'm going to consider terms like quadratic in phi. Okay, but this is generic. You can use phi 2, 4 and phi 6. But I'm just concentrating on phi squared just to illustrate the model and the ideas of those normalization and the parameter couplings or parameters of the theory. So one of the things would be like say sorry, say c naught phi phi d squared phi c1 phi squared c2 phi d4 phi and so on so forth. So my model is like this. Okay, modelটা কিরকম যে এখানে c0 c1 c2 these are parameters of my theory. c0s are basically g's. Okay, so you can call them g's as well. Phi's are my fields and these are derivatives. Okay, so this is nothing but the quadratic term d phi squared term. Okay, এটাকে আমরা by modulo what is called pattern, yeah, by modulo what do you call somebody help me out here. I forgot the name of phi d phi. Okay, integration by parts. Okay, by modulo integration by parts. Okay, I forget the name, but I wrote the thing right. Okay, so this is like at the boundary, and at the boundary phi vanishes. So you would get this. This is nothing but the quadratic term in your Lagrangian, okay, which we wrote earlier. এটা হচ্ছে ম্যাথ টার্মের মতো, ওটার সামনে একটা প্যারামিটার, আর এগুলো হচ্ছে হায়ার অর্ডার ডেরিভেটিভ। ওকে, দে ক্যান বি ইন ইউর থিওরি, মানে ইন জেনারেল কেউ তো মানা করে না। ওকে, সো সুমিত আরেকটা কোয়েশ্চেন, সুমিত, another reason might be using the even powers is that because it's a phi theory, it doesn't matter because it's a scalar already. But if you are working with like size, spinors or vector fields, you have to consider like even power, something like that. Mane, you cannot have indices, right, because of Lorentz invariance. So yeah, the symmetry properties will constrain your theory a lot. Yeah, but yeah, conductivity people might not care about that, right, because they are doing non-relativistic, right? They have to care about like Galilean invariance. Okay, so okay, so please ask me questions at any point if you have any confusion. This is the model probably I can try to do in this talk. Okay, I'm not sure I'm not going to mess up, but let's try not to mess up. Okay, so এটাকে আমরা Fourier transform করব. So phi x, we're going to Fourier transform it and Fourier transform it by d for I'm forgetting those 1/2 pi factors. They are not important for the philosophy of the problem or the model. I'm just Fourier transformation এটা বসাচ্ছি. So let us do the simplest thing for the demonstration. Other things you can figure out. So let us do like C1 pi x squared, pi x term. So C1 is a constant. So I'm not going to write it from now. I'm just going to write the relevant terms. It's a constant, so I can write it like outside. It's constant. It's a coupling. It's a parameter. Okay. Initially, it doesn't depend on any space-time point. That's also an assumption. So if you do this thing, you would get a delta function, delta of k plus k prime. And if you drive away the k prime integral, you would end up getting phi of k, phi of minus k. Okay. So that's how you would get this kind of term. Okay. Phi of k, phi of minus k. Okay. All right. And from the Fourier term, okay, so how do you see? Okay, so if you write phi of x, and if you demand because e to the power minus ikx phi of k, okay. If you demand the complex conjugation and and the original field should be same. If you demand that, তো তুমি দেখতে পারবে যে এই সাইনটা চেঞ্জ হবে, কে মানে এটা প্লাস হয়ে যাবে, বাট তুমি এই প্লাসটাকে অ্যাকোমোডেট করতে পারবে মাইনাস লিখে এখানে কেটাকে যে মাইনাস করে দাও। ওকে, so that's why we say complex conjugation really amounts to মানে complex conjugation and the phi are same. That means the reality condition really amounts to saying that phi star k is nothing but phi of minus k. Okay, and with the delta function you also saw that how phi of minus k came in. So because they were already scalar, I'm going to phi star phi again. Okay, so then I can write my my action as to be TDK f of k squared phi of k phi of minus k. So I packed all my parameters into this f of k squared term. Okay, so f of k squared term is nothing but c naught, it's a power series expansion, Taylor series expansion, c1 k squared c2 k to the power 4. So how do you কিভাবে আমরা এগুলোকে অ্যাসোসিয়েট করব? So c naught term has phi k phi minus k term, nothing else. Okay, just আমরা যেটা ইন্টিগ্রালটা করলাম, এটা k স্কয়ার কেন এসেছে? because there are two derivatives. ডেরিভেটিভের ফুরিয়ার ট্রান্সফর্ম করলে হয় k স্কয়ার with a sign. K4 are other higher order terms. Okay, so there will be, so you can see this easily that this function, this f of k squared to be a function of momentum squared. Okay, squared because as I and Shumit are talking about, this is because of symmetry, quadratic symmetry or rotational symmetry, or Z2 symmetry basically means up down symmetry, which is a symmetry of Ising model. We'll talk about a bit about that, and probably a little bit about block spin if time permits. Okay, cool. So let's move on. So my partition function looks like, I'm going very fast, I guess. So if you don't understand at any page, just tell me that I'm going too fast. If you don't say anything, I would assume that I'm doing fine. And also because I'm worried that I am annoying too many people around. Sorry. Because I'm literally outside. Okay, so all right, so exponential উপরে টার্মগুলো ছিল, so now I'm writing আমি d phi টাকে okay, so path integral d phi is a measure which is okay, মানে d phi আমি এখানে phi i না বলে phi xi বলা হচ্ছিল, মানে there are a lot of fields that every point there are many fields, and d phi is actually the combination of all those phi i's. Okay, so this is how d phi really means, path integral measure. Um, it's a lot of multiple integrals you can think of. Path integral, if the word path integral is a fancy word, then it's like multiple integral, a lot of fields at a lot of points. So that's why. And then you write it down. The ddk squared, f of k squared, phi of k, phi of minus k. Now, so okay, that's written. এখন যেটা করবো, so we initially had a lattice spacing which is a. Okay, so that was initial lattice spacing. And also let me make a comment about k. So this is whole dimensionless because I'm considering my k to be a dimensionless quantity. Okay, so let me call another quantity. Let me use another quantity called q. Define it. Q is something which is k and a. Okay, this is a dimensionless quantity. Why? Because momentum has inverse length dimension. A has a dimension of length. So q is dimensionless. Okay. So you can rewrite this whole thing in the terms of q and that dimensionless quantity. Man, I'm saying that I'm like, yeah, per lattice point. So if I increase my lattice point, man, I increase the distance in my lattice, increase my size of lattice separation. So I mean, A-take, let me multiply with B. Okay, let me make it like AB. Okay, I multiply this thing by B, and I increase my lattice separation. My spins are like very far separated. Okay, in that case, you know, my momentum, okay, would go like Q over B. Okay, so initially যদি আমি আমার এই জিনিসটাকে এভাবে নরমালাইজ করি, okay, so my integral আমি যদি এভাবে নরমালাইজ করি, তো my integral হবে 0 to 1. Okay, but because I'm doing this now, মানে I'm changing my scale, this is called this is one of the RG transformation. So আমি মাইক্রোস্কোপিক একটা থিওরি থেকে শুরু করছি যেখানে ল্যাটিস স্পেসিং ছিল a. Now I'm increasing my lattice space. Okay, so okay, by increasing my lattice spacing, so that's one of the RG transformation. Okay, so আমি zoom out করছি আর কি. So আমার macroscopic physics তো zoom out, right? Microscopic physics is like zoom in. So if you zoom in, you see many details, and you see the granular structures. If you zoom out, you see the mean field theory structure. It's kind of like that. So আমি এটা করছি এখন. Okay, so এটা করলে, let me define another field. So আমার then my integration measure would also change. So it will be like 0 to 1 over b now. Okay, so it picks up some dimension. So let me now define another dimensionless quantity, another dimensionless momentum, let's say p, and let's call it um, qb. Okay, so let me see. Q ranges from like 1 over b. If I multiply q by b, sorry, if I multiply q by b, q with b, what happens? Q picks up a dimension 1 over b, right? Because I changed my length scale. My length scale is a k ab kori, মানে separation টা যদি আমি ab kori, then my q changes to 1 over b because, you know, separation and moment are opposite. So this picks up a dimension, this gets rid of that, and it's dimensionless. So my range of momentum integration again becomes 0 to 1. Okay, is that okay?
Yeah.
Okay, yeah. So all right, so so let us break down my field. Fieldটাকে আমি মোমেন্টামের বেসিসে, মানে in terms of momentum I'm breaking down my field. Okay, some are fast, some, so my integration, so what do I mean by that? So my integration, so I'm writing the s, which was 0 to 1 over b dq, d dimensional q, f of q squared, f of phi of q, sorry, phi of q, phi of minus q. Okay, now I can break this up into two pieces. Okay, one of the piece would be, say, 0 to 1. Sorry, আমি একটু ভুল করছি এখানে. I said something wrong. Yeah. Let me think about it. I think I should. Oh yeah, right. Yeah. Now I can separate my field. Yeah. Okay, fine. Okay. Fine. Let's go on to separating the field. Yeah. 0 to 1 over b. Now, because I take a dimensionless quantity p দ্বারা যদি করি, so let me do this thing. Sorry. Let me do this thing. So যে এখন যদি I use this new momenta qb, then I can so this limit now becomes 0 to 1. So I can separate this thing like 0 to 1 over. Okay. In the q integration. So b part plus to 1 part. Okay. All right. So well, if I change the scale, I think I messed up a few things here. If you change the scale, then with the cutoff. Okay, so what I'm doing here, I'm okay. So let me give the so let's get the philosophy right. So what is happening here is J. So B, I have changed my cutoff. Okay, so by changing the lattice spacing, so there is a cutoff between 0 to 1 over B, and there is one cutoff is 1 over B to 1. Okay, now 1 over B to 1 is a higher is a higher in the momentum scale. There would be the higher cutoff. Okay, so what does that mean? Okay, so let us try to have an idea. So if you change the scale, if you change lattice spacing to AB, but means you multiply by B, your cutoff momentum cutoff lambda would go like lambda over B. Okay, so all right. So if this scaling, you can scale up or scale down. Okay, so if you scale down, then the cutoff will increase, and if you scale up, when you increase the B, then cutoff will decrease. All right. So in our case, what term should we drop off in the integration, and what we can perform? So there are I'm increasing B. I'm going to the do I want to look at the infrared behavior? Yeah, so I'm neglecting the short distance physics. Okay, so I'm going to integrate over like 1 over B to 1. So this is my short distance stuff. I'm going to integrate over this thing. That means integrate over this stuff. dq f of q squared phi of q phi of minus q. Okay, so okay, so I'm going to integrate over this. After breaking it up, I'm going to integrate over d phi, where q runs from 1 over b to 1, d phi of q's. Okay, with those q's who has values 1 over b to 1, and the e to the power minus integration d dq f of q squared, sorry, phi of q phi of minus q, and it would range from, say, yeah, the same thing, minus b to 1. Okay, so this is a quadratic integration. Okay, and we can do this integration. It would come out to be some square root pi over alpha Gaussian type f of q square contribution. Okay, some scalar. Okay, we can do this integration, and because so this part is gone. Okay, this part is like gone now. Okay, we integrate over. So this is called integrating over. Integrating over the region 1 by b to 1. We integrate over that part. Okay, all we are left out is between 0 to 1 by b part. Okay? So we break down our 0 to 1 into pieces like, because our scaling change করছি, so I can change my integral sign to 1 over b plus 1 over b to 1. Okay, so you need, I mean, okay, I scaled it up and then I broke it up. So I changed my lattice spacing, then I redefined my momentum. So I got to 0 to 1 and then I broke it up 0 to 1 over b and 1 over b to 1. Okay, then I integrated over this part. Okay, and I'm concentrating on this part of physics. Okay, this is the low energy physics that it contains. So I'm looking at that physics, what are the relevant and what are the irrelevant terms. Okay, so this is a path integral integration যেটা আমরা করলাম Gaussian দিয়ে বা whatever, basically Gaussian. So that part is gone. Okay, but because of changing the scale, okay, so you might say, okay, so what is the contribution of changing the scale? You are integrating over this part by breaking it down, but what about this part of the scale? Okay, so what is the influence of this part and this part? Of course, high energy theories should have a signature on the low energy physics. Okay, so what is happening and what is the signature there? So that signature is given by the scaling thing which we did. Okay, scaling এর মাধ্যমে আমরা যখন আমাদের a কে ab করছি, so our q become p, which is qb, became this. Well, basically q over b, but we defined it as dimensionless way. Then our field phi should also be changed. Okay, should also be changed, and we change it by d by 2 by 2 psi of p. We define it like this. Okay, so our scale changing ta, okay, my scale changing actually induced a change in my fields. Okay, I have to change my fields as well. Okay, so basically this integration which I have done, it has to be done with this psi of p. You write down psi of p, you include this thing, and then you integrate over 1 over b to one part, and then you concentrate on this part 0 to 1 over p, 1 over b, sorry. Okay, why 1 over b? Because it's a momentum sector we're working on. Okay, so what happens in, so this part is the আমাদের, so there will be this pi over f of q squared term, yeah, where q squares are such q square, the other value qi er value, sorry, looks like a pi. Qi er value is from 1 to 1 over 1 over b to 1, and then the integral is there, and there are other measures where qi er value from 0 to 1 over b, and because I'm increasing b, I'm like lowering my momentum. So yeah, okay, sorry, minus 1 over, sorry, f of q squared phi of q, phi of minus q, d dq. I can't write d dq. Okay, yeah, I could write it. Yeah, okay, good. So okay, so I have to change these things. Okay, so first of all, what I have to do, dq becomes dp. Okay, and it becomes b to the power d because of p is equal to qb. Okay, I think I defined it wrong. I think like p is equal to, like I said, q by b, so q is equal to p over b. Yeah, it's right. Yeah, so it's like a minus. Sorry, it should be minus. Yeah, and then phi of q's, they should also be changed and should be like sorry, b to the power minus d plus 2 by 2. So why b to the power this? Because if you do the dimensional analysis of fields, so just give you a hint why I'm doing what I'm doing. It's not arbitrary. I spent a few times today just to understand myself. I forgot that you can dimensional. So you have to check the dimensions. Okay, check the dimensions of phi of q. Okay, check the dimensions of phi of k. Okay, and also these lattice things. And there are the space dimensions. You have to absorb them. Okay, so if you ignore those subtleties, you'd be able to just or take some of my words for granted, which are not logically at conflict. Then we can go ahead. Okay. If you have any questions, you can ask also. People are very silent. Can you hear me? Is my internet connection all right? Now I'm running on with my mobile internet, so I'm not sure. Is it all right? Probably মৌনতা সম্মতির লক্ষণ. So for phi, this is definitely not true, but in this case, this is what I have to assume. Okay, so I'm writing this down. Yeah, so if you plug these values in, then you would get আমার এখানে দুটো টার্ম আসবে মানে because there are two b's coming from two phi's, 2 cancels out, minus d minus minus 2 and psi of p, psi of minus p. Okay, so this comes here. This psi has nothing to do with spinors. Okay, this is just we phi টাকে redefinition করা হয়েছে. So you see the idea of what is renormalization doing. You change the scale, and changing the scale amounts to the redefinition of the field. Okay, then you integrate over like high energy results, okay, that we don't know, and there is a cutoff there, and that scale change induces something, sorry, so something which we are going to now see. Okay, sorry, so this is encoded in here, and this is encoded, it's the high energy stuff, they're encoded in here, and they also encoded in here. So okay, so I think I have to be careful with the signs here. So probably I have to work with, probably this is a plus sign. Okay, আমার মনে হয় psi p কে minus b করতাম, so this is plus sign. Yeah, why I'm saying it a plus sign, because I have to cancel this and this. Okay, the whole dimension works out that way if you calculate it properly. Okay, so yeah, so I have b squared and everything else is like, okay, so let me write it down. So what is left over is something junk যেগুলো আমরা আগের পেজে লিখছি. So let us have a look at the junks. This is the junk I'm talking about. This is the whole junk I'm talking about, except for z. Z would be equal to. So this is a junk I'm not going to write, but I'm going to write something which is relevant. Okay? Just have a look at the junks. Okay. Okay. Cool. So this is okay. So the junk. If there are any string theorists out here, it might kill me calling high energy physics junk. All right. So what I'm doing? Okay. So I'm going to write it down, and dq product and a glass e to the power minus. So you have b squared. Okay, you have b squared, you have dd well dp psi of p, psi of minus p, and f of p over b. Okay, p over b. Okay, right. So now changing the I did a few things. Okay, আমরা field redefinition করছি. Okay, and we plugged in the value, we plugged in the change of the momentum due to the change in the scale. Okay, now if you compare this, okay, so that is called a rescaling, or redefinition of the field, or rescaling. If you do this stuff, then you compare it with the original stuff. Okay, they will look the same. Okay, original যদি আমরা start করছি, so you equate this with the original stuff. Okay, original stuff মানে z সমান যেটা আমরা start করছিলাম, some stuff e to the power minus s, যেটাতে f of q square দিয়ে লেখা হয়েছিল, f of q square phi of q, phi of minus q. We will compare, so this will they will now be compared. Okay, and you see there is a change here. Okay, because as এর মধ্যে এগুলো ছিল, এখানে কোনো b square term ছিল না, so there is a b square term, q squared এগুলো আছে, বাট এখানে কোএফিসিয়েন্ট গুলার সামনে কিছু ফ্যাক্টর আসবে, এখন এখান থেকে ফ্যাক্টর আসবে, এখান থেকে ফ্যাক্টর আসবে, এগুলো এখানে ছিল না। বাট এই phi q আর p কে আমরা এখন সেম করতে পারি, কারণ হচ্ছে দেয়ার ইন্টিগ্রেশন মেজার দ্য সেম। ওকে, কারণ এটা ডামি ইন্টিগ্রাল, আমি p এর উপর ইন্টিগ্রেট করি, q এর উপর ইন্টিগ্রেট করি, দ্য সেম থিং, রাইট? বিকজ ইটস ডামি, লাইক ডামি, I don't know who I am, something like that. Dummies are integrated over. Okay, so let us equate the coefficients for both cases. So for our new case, we have this b squared f of p over b. So this is the relevant term. আমি এটা লিখতেছি, সাথে phi square term গুলো আছে, but they are, as I said, less relevant. So this will turn out to be c naught plus c1 p squared over b squared plus c2 p to the power 4 by b to the power 4, and so on and so forth. Now b squared termটা যদি আমরা, if you multiply with b squared, then it's c1 p squared by b. So this is dimensional, this is, sorry, there is no p, there is no b squared, because b squared cancels out, and then c2 p4 p to the power 4, to the power 4, and b squared. Okay, and the other terms are there. Okay, now you compare this with, so এটা যদি আমার okay, so if you compare with the original term, you see c naught prime is changed to c naught b squared, So let us call this C naught prime. কারণ এর সাথে হচ্ছে momentum 0 টার্ম হচ্ছে এটা momentum square মানে আমার যেহেতু quadratic function আমার ফার্স্ট অর্ডার আমি p square. So C1 prime is actually C1. C1 term is not affected. C2 term, C2 prime is actually what? B to the power minus 2. B to the power minus 2, C2. Okay. So from here, I can write a recursion relation, which is okay. So we can write a recursion relation to Cn prime, Cn b to the power 1 minus 2 times 1 minus n. Will this work? Like if you put n equal to 1, if you put n equal to 0, you have b squared. That is all right. If you put n equal to 1, you would have b to the power 0, c1 prime equal to c1. That also is all right. If you put n equal to 2, that is minus b squared, c2 prime. That is also all right. Okay. So if three of them are all right, induction, that would work all right. So this is the recursion relation. So this is what we find by the RG transformation. So what the RG had, মানে RG আসলে কি করছে? RG transformation কি করছে? আমরা একটা original theory দিয়ে শুরু করছিলাম, okay, which was a bare theory, which was defined for all momentas and all that. তারপর আমরা স্কেলটাকে বড় করছি, মানে আমি শর্ট ডিসটেন্স কে লং ডিসটেন্স করার ট্রাই করতেছি, মিন ফিল্ড থিওরি করার ট্রাই করতেছি, লো এনার্জি ফিজিক্স চেনার চেষ্টা করতেছি, হাই এনার্জি ফিজিক্স ইন্টিগ্রেট আউট করতেছি। So all that amount of doing is the redefinition of the parameters. Okay, এটা যেটা করছে, এই যে ছাপটা রাখছে হচ্ছে প্যারামিটার। Okay, যে হাই এনার্জি ফিজিক্স এর যে রিডেফিনিশন গুলো হচ্ছে, these are in the parameters or couplings in your theory. Okay, that's the takeaway message. And the steps are that you do some scaling transformation that induces some changes into the momentum. Okay, and then it also induces some changes into your fields, and you redefine them, you rescale them, and you see this thing. Okay, you compare and you see the coupling change. Okay, মানে there are two to three steps. One step is scaling, then field redefinition, then rescaling of your limits, so that you can compare both the integral measures, and then you read of the coupling changes. Okay. All right. So that's about the idea. So what we can learn from this thing. Okay. So এখানে C naught prime, you can see C naught prime is actually b square C naught. তার মানে আমি যদি আমার length b টাকে আমি আর what is b? B is a generic thing. Okay. আমি আমার স্কেলিং, আমার সেপারেশন ছিল a কে আমি ab করলাম, পরে আমি ab স্কয়ার করলাম, পরে আমি ab কিউব করলাম, abn করলাম। Okay. So b is just a quantity that you multiply, by which it's kind of a picture of Kadanov block spin, what Sumit and I was talking about. We are zooming out the same amount. Okay. So আমরা হচ্ছে b টাকে যদি অনেক বড় করতে থাকি, আমার c naught term gets bigger and bigger and bigger and bigger. So this coupling is very important. Okay. As you zoom out, this c naught coupling is very important. It actually grows. Okay. It grows with each of your RG transformation. So this is very important. What about C1? So this is called a relevant operator. Technical term. Okay. Relevant operator. You cannot ignore this coupling. এই couplingটাকে ignore করা যাবে না। যদিও it is a constant term. So and it is multiplied with phi squared. So anybody can guess what this term might be associated to any physical thing. It multiplies the quadratic field, and it's a constant term.
It's mass.
It's a mass term. It might, yeah. So yeah, it's a mass term. So it grows with your. Okay, so and we also saw probably. C1 doesn't change. We saw. So C1 doesn't change with your scaling. তার মানে এটা সম্পর্কে তুমি বেশি কিছু বলতে পারতেছো না। So it's like the boundary of your analytic function that you define is convergent or not. The boundary, you don't know what is happening at the boundary. Okay, so this is like a marginal operator. Okay, it can be relevant, it can be irrelevant. Okay, at the boundary of analytic function, the function can converge, can diverge, we don't know. So this is in the same sense as marginal. Sorry, yeah, marginal. I'm sorry, but yeah, I think you can read it off. And C2 goes like C2 C minus. Okay, inverse of B power. That means as you increase the B, আমি যদি B কে 1000 times করি, this will be like so insignificant that they will not be important. Okay, so RG transformation হচ্ছে this যত RG transformation করব, এই প্যারামিটার গুলো তত বেশি unimportant হয়ে যাবে। Okay, this you can throw them out. Okay, so the relevant is there is only one parameter which is very relevant, that is C naught, and there is a C1 which can be relevant. Okay, so this is the idea of a RG transformation in short. Okay, and yeah, so let me give you a quick view what we have done there. এত calculation আসলে কি করলাম আমরা? So a quick summary হচ্ছে, let's write down the action. It is dimensionless. C naught phi x squared. Now I'm writing in the position space, so I should not be using the q. I should be using the x. C1, okay. D phi x squared. C2 phi to the power 4, and so on and so forth. Now, in D dimensions, phi has a dimension of d minus 2 by 2, right? তাহলে phi square has a dimension of d minus 2, আর এটার dimension হচ্ছে minus d. The d cancels out. তাহলে c naught এর dimension হবে plus 2. Mass dimension is plus 2, or minus 2. Well, mass dimension is plus 2. Yeah. Does it? Well, I have to think a bit. Oh. D minus 2 by 2. I have two squares. 2 cancels out. I'm sure. Okay, let me come back to this one. Yeah, it should have mass dimension plus 2 because. So did I do something wrong there? I think we're doing the momentum there. Okay. Yeah, we're doing. So let me check back. আমি মনে হয় একটা ভুল বলছি জায়গায়। এখানে না। আমি erase করে দিচ্ছি ওই প্লেসটা। Which one was that? This one. Yep. It's actually growing with the separation, so it's not. It behaves like a mass term. It should have mass dimension minus 2, right? Yeah. Yet I'm saying that it has a b dimension b squared. So it's like b squared. So what is happening here? Well, this has to be. It will be in the definition. It should be minus 2. Am I missing something with the C naught term?